So I've added a few more class meetings and all that kind of stuff. I'll fill out the remaining 17 probably this weekend. One thing that is here that was not here earlier today is this thing called exam study materials. There are 3 different folders in Moodle, each containing old exams. There are 3 old exam 1s, there are 3 old exam 2s, and there's only a single old exam 3 up here right now. So I will endeavor to work on that. I do want to say something. I believe that all of the old exams that I've posted to this point are back when I was effectively giving 3-hour exams, and I've been told to stop doing that because it's mean. So there are 10 questions shorter now. So I believe all of these were 35 questions long. Your exam will only be 25 questions long. That being said, everything I've posted up here is fairly representative of the type of questions I might ask. I will obviously just have to eliminate some of the questions, okay? I wrote all of these old tests. I am writing all of the new tests. So if you want to know the kind of mean crap I put on an exam, this is where you will find it. In my opinion, these old exams, as well as the in-class assignments, are the best way to study because that's all of the stuff that I wrote. If there is a homework problem that I like, that I tend to put something very similar to that on the exam, I usually let you know. That's really not going to happen until we get into the capacitor and inductor section, which is well into the exam 2 material. So your exam 1, which is a week from Monday, just so we're all very, very clear on that. You have all of your study materials up here. I have also uploaded all of the solutions to the in-class assignments up to this point, and I will have the remainder of them up over the weekend where they will automatically open 1 minute after you were supposed to turn them in on time and all that kind of good stuff, so that I can't forget to provide those to you to study for, okay? So all of that to say, you have been provided materials for which to study for your exam. You'd be a fool to not start studying now. All right. So, lecture material for the day. We are going to be learning about nodal analysis. Nodal analysis is really an algorithm that will allow you to perform a series of steps to analyze practically any linear circuit and determine any voltage in that circuit. William, you have a question? Okay. So what I'm going to do is I'm going to put a circuit up on the board, and then we're going to learn by experience, working our way through the steps, and I will detail them all. We are going to start with a circuit containing only current sources, learn the basics, and then we are going to have to modify our approach when we include voltage sources. And the reason for that will be obvious as soon as we try to apply our analysis technique to something containing a voltage source. Okay. So our circuit of interest for this first iteration of nodal analysis will be this guy. So this is the circuit that we are going to be analyzing, and I would argue it's probably more difficult than anything we've seen to this point, except for maybe a couple of the homework problems from homework set number 5, where it asks you to do superposition on something that looks similar to this, which is utterly asinine. You should be performing nodal analysis or mesh analysis on anything that looks like this. We'll talk about that in a little bit. Okay. So our first step is to simply identify all of our nodes. Okay, so I'm going to do that using the various different colors, exactly like I have done every other time we have identified nodes. So I have a node on the top left that I've put in red. I have a node on the top right that I have put in blue. I have a node here in the middle of the circuit that I've labeled in pink. And I have a node here on the bottom of the circuit that I've put in green. And now what I'm going to do is I'm simply going to define them as, let's call this guy in red node A, this guy here B, and this guy here C, and this guy here D. Okay, so that is step 1. Hopefully we're all kind of well aware of how to do this step at this point in our circuit analysis careers. We've been doing things like this in our resistor combination techniques. We practice this literally on the first day of class. Step 2 is going to be something new. We need to select a reference or ground node. So what I mean by this is we pick one of these 4 nodes in this circuit, and it will be the node that serves as a reference for all of the other nodes. And what we are going to do by selecting it to be ground is effectively saying that the voltage at this very specific node that we pick is 0. And then all other nodes will have voltages with reference to that 0 point in our circuit. Okay? Nodal analysis will work regardless of what node we choose to be our reference. Any 4 of these are valid choices because any node is a valid choice for our reference nodes. That being said, there are times when choosing a specific node will make the circuit analysis easier. Because we don't have any voltage sources, this is not one of those times, okay? So when there are not voltage sources, what I typically do is choose the node that has the most elements connected to it to be my reference node. But as you can see, for this particular circuit, every node has exactly 3 elements connected to it. So we can choose any of the 3 nodes and we will get the same results regardless. So somebody tell me a node that we're going to serve as reference. Raise your hand if you want A. Let's do this democratically. All right, so like 6 people for A. How many for B? Also 6 people. Great. How many for C? Like 5 people. All right. How many for D? A shitload more. So we're going to go with D. The bottom as the default is the probable most obvious choice. Okay, there are times where it's not going to be the best choice, but the overwhelming majority of the time you can choose the bottommost node and it'll be reasonable at worst. Actually, I say that any node is reasonable at worst. So I'm going to replace this letter D and I'm putting the ground symbol here. So this node D, we are assuming has a voltage of 0 volts at it. And then all of our other voltages, which we'll talk about in just a moment, will be in reference to that. So step 3 is to assign our nodal voltages. So this is how we're going to do it. Every node that we have identified that isn't our reference node is going to get a voltage. So node A will have some nodal voltage VA. Node B will have some nodal voltage VB. And node C will have some nodal voltage VC. Now let's talk about what this concept of a nodal voltage means, okay? So this description, VA, VB, and VC, all of these voltages are with respect to ground or with respect to our reference. So the nodal voltage VA is the potential difference between this point and this point in our circuit. So another way to express that would be voltage drop across the 10 ohm resistor. Because the positive polarity terminal of the 10 ohm resistor is node A, and the negative polarity terminal of that voltage that I've drawn is associated with node D, or our reference node. Similarly, VC is the potential difference between these 2 points, which would be the voltage drop across our dependent current source, positive polarity on top. Okay. And then obviously our nodal voltage VB is the voltage drop across the 2 amp independent current source in the middle, positive polarity on top, ground on bottom. Okay. So for a nodal voltage, the node at which we've defined the nodal voltage is the positive polarity terminal of the voltage. Ground is always the negative polarity terminal of that voltage. Okay. All right. So what we are going to do now is we are going to move along to step 4. In step number 4, we are going to define our controlling variables in terms of our nodal voltages. Okay, so I've used a new couple of words here, controlling variable. So what I mean by controlling variable is if we have a dependent source, which we absolutely do, the controlling variable for that dependent source is the voltage Vx, okay? Vx, the voltage drop across the 15 ohm resistor, positive polarity on the right, negative polarity on the left, controls the output of that dependent current source on the bottom right of the circuit. So our goal here is to express the voltage Vx, the voltage drop across the 15 ohm resistor with the positive polarity on the right and the negative polarity on the left in terms of our nodal voltages, okay? So I'm going to do that in a different color. So we are going to have Vx is equal to something, okay? So for voltages, this is very straightforward. What nodal voltage is associated with the positive polarity terminal of the voltage Vx? Vc. what nodal voltage is associated with the negative polarity terminal of Vx? VA. It is always positive polarity nodal voltage minus negative polarity nodal voltage. Always, always, always. It will never, ever be anything different than that. Okay. So we have defined our controlling variable in terms of our nodal voltage. Just for the sake of argument, let's look at something slightly different, okay? So let's say that I had a controlling variable that was this current IY. We're not actually going to analyze this, but I want to explain how you would do this, okay? We are going to use Ohm's law, okay? So we could say that IY is just the voltage drop over the resistor that the current is flowing through divided by the resistor value. Well, if we look at the direction of IY, and we know that our resistor needs to be absorbing current, the positive polarity terminal is what? Is it node A or ground? Positive polarity terminal would be associated with node A. So that would look like VA. Where's the negative polarity terminal for that 10 ohm resistor? Ground. So -0 divided by the resistor value. And when you're more comfortable, you can literally just call this VA over 10 ohms. Okay. So when we have a controlling voltage, it's just going to be the difference of two nodal voltages. Whenever we have a controlling current, it's going to be the difference of two nodal voltages divided by a resistance, because Ohm's law tells us it has to be that way. You guys are going to make simple mistakes. The nodal analysis process, we are going to have a lot of terms that looks like what we just did for IY over and over and over again. And so when you get a controlling voltage, some of you by gut reflex are going to say that it's a difference of voltages divided by a resistance. And that is always going to be wrong, because a difference of voltages divided by resistance is current, okay? So when we're trying to define a voltage in terms of our nodal voltages, resistance should not show up in the equation at all. I'm just warning you about that now, because you're going to make that mistake. It's an easy mistake to make, okay? All right, so what we are going to do now is step number 5. We are going to write a KCL equation at all non-reference nodes. So we never write a KCL equation at ground, but we write it for every other one. So in this circuit, there are 3 nodes which are not ground, so we will have 3 KCL equations. Okay. So let's start, and I'll do this in blue. So KCL at node A, okay? So how I like to do this is I literally put all of the currents that are leaving node A, okay? So there is a current that branches from node A and flows down. There's a current that flows to the right, and there is a current that flows up. So I'm expecting my KCL equation at node A to contain 3 terms. I'm going to add those 3 terms together and set it equal to 0, because that's what Kirchhoff's current law does, okay? So let's start with the current directed down. What is that current directed down in terms of our nodal voltages? VA over 10. We literally just did it when we defined IY. There was a reason why I chose that, right? So that's the rule that we are going to follow. VA over 10 ohms. And then we will have our next term, which is the current directed to the right. So based on what we did here when we defined IY, who can tell me what they think the current directed to the right through the 5 ohm resistor should be? Exactly correct. VA minus VB over 5 ohms. This is nothing more than Ohm's law. Let me rewrite this A so that it doesn't look like a delta, which shouldn't have been an issue, but I just want to make sure that we're okay. So when we are writing these KCL equations, we are doing so with the assumption that the node that we are applying KCL at is the positive polarity terminal of any resistor that we see. Okay, so what about the current directed up through the 15 ohm resistor? Say it louder, please, Thomas. So I disagree. VC minus VA over 15 ohms would be the current flowing from right to left through the 15 ohm resistor. We're looking for the current that flows from the left to the right. So it should be VA minus VC. Effectively, let's write that down real quick. VA minus VC over 15 ohms. So when we write KCL at node A, all of our node A terms should be getting a positive sign, and every non-node A term is the one that should be getting a negative sign. Now that can change once we have to include dependencies and all that kind of stuff, like when we substitute controlling variables in and stuff like that. But for our bare bones equation here, that's the way that it's going to work, okay? So effectively, where the current starts at minus, or the node that the current starts at minus the node that the current is going to, divided by the resistor value. Always, 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 okay? So we have now written 3 terms here, and we were expecting 3 terms. So we set this equal to 0. That is our first equation. Now let's do KCL at node B. So I'm going to have this current directed to the right, this current directed down. Excuse me, the first one I said was to the right, but it's obviously to the left. The one directed down, and now the one directed to the right. So, Macy, what do you think the current flowing through the 5 ohm resistor from right to left should be written as? I understand fully that this is the first time you guys are seeing this, so I am expecting mistakes, okay? I'm not trying to put anybody on blast. I'm just trying to make sure that it's clear to everybody. So making a mistake allows me to explain it again. Exactly correct. VB minus VA over 5 ohms. Wonderful job. Now, the current down. Jacob's smart, right? Tell me what the current directed down leaving VB is. But it's not a resistor. Okay, so exactly right. So the current source tells us that there is 2 amps of current flowing up. We are interested in the current flowing down through that branch, which is just going to be negative 2 amps. It has to be the exact same magnitude, but in the opposite direction, okay? So you're 100% correct. If we have 2 amps up and we're interested in the current flowing down, it's just negative 2 amps. Good job. All right, and now we need the current flowing to the right. Jake, what's that going to be? Exactly correct. VB minus VC over 20 ohms. Is equal to 0 because we were expecting 3 terms. Now let's do KCL at node C. So that's going to be this current directed to the left, this current directed down, and this current directed up. Sully, what is the current directed to the left? Exactly correct. VC minus VB over 20 ohms. Reagan, what's the current directed down? .5 Vx, yeah. So anytime we have a current source, it's just going to be the value of the current source. When it's in the same direction, we leave it alone. When it's in the opposite direction, we throw in a negative sign. So you're 100% correct. The current flowing down from VC is just going to be 0.5 Vx. And Cameron, what is the current flowing up, leaving VC? Exactly correct. VC minus VA over 15 ohms. Is equal to 0. So we have written, Daniel, you have a question? We were going to handle that in about 10 minutes. Yeah. Not at all. Wouldn't change a single thing. Any other questions? All right, so at this point, we are ready for step number 6, where step number 6 is simply solve the system of equations. Okay? Now, I want to talk to you guys about something here. So let's put step number 6. How many equations did we write? I disagree. We wrote 4. This one up here is part of that system because we have a dependency here on Vx. Okay? So we can either do a simple substitution everywhere we see Vx, we replace it with Vc minus Va, which would give us a 3-equation, 3 unknown system. Or if you have a Casio 991 calculator, you can just leave it as a 4-equation for unknown system, okay? That's why I encourage you all to buy that particular calculator to solve systems of equations. So I want to talk about this very briefly for your exams, okay? I will not give you any problem that requires you to be able to solve a 4-equation for unknown system. I will absolutely give you something like this, where a simple substitution or two will reduce your system of equations down to a 3-equation, 3 unknown. So 3-equation, 3 unknown system is effectively the benchmark. Your calculator needs to be able to do that. And to my knowledge, pretty much every calculator that is on the NCEES approved list does it. I know that these TI-36 do it. I know that these Casio 115s do it, but the Casio 991s are capable of doing 4 equations for unknowns, okay? It is the most powerful calculator with regards to solving systems of equations that you are allowed to use on any of these exams. In my opinion, it is well worth the modest $20-ish price tag, okay? Not saying you can't get by. In fact, I gave mine away to a friend. I'm so used to using these two. But I really do recommend the Casio 991 for this portion of the class. All right, so we're going to solve this system of equations. I am going to write down effectively a matrix here. We're not actually going to solve it using any matrix manipulation or anything like that, but we are just going to figure out what the coefficients that need to go into our calculator are. Now, thankfully, our calculators are pretty smart. So in our coefficient matrix here, there's going to be some math that the calculator is going to do for us. So we don't have to put in a specific numerical coefficient. We can put in a combination of coefficients, so let's say 1/10 plus 1/15, and the calculator will take that as the coefficient for VA and be able to do everything perfectly well, okay? So because I only have 3-equation, 3 unknown calculators on me, we are going to make that substitution where we say that Vx is VC minus VA. Let me just double check that here, okay? And I'm going to have to do a bit of flip-flopping back and forth to write my matrix, but it'll be okay. So the coefficient for VA in my first equation is going to be 1/10 plus 1/5 plus 1/15, because everywhere I see VA, that's what it's being multiplied by. So I'm going to have 1/10 plus 1/5 plus 1/15. That's my coefficient for VA. My coefficient for VB for my KCL at node A equation is just -1/5. Everybody see that? My coefficient for VC from my KCL at node A equation is just -1/15. Sorry, I scrolled slightly too far. This matrix is going to be VA, VB, VC. And this column is where we're going to put our constant terms, right? So there are no constant terms in our KCL at node equation, or KCL at node A equation other than 0. So on the right-hand side here, this guy is going to be 0. Now let's look at our KCL at node B equation. What's our coefficient for node A, or for VA? -1/5. What is our coefficient for node B? Exactly correct. 1/5 plus 1/20. And our coefficient for node C in our KCL at node B equation is Negative 1/20th, absolutely right. So this KCL at node B equation does include a constant term, right? There's that factor of -2 amps. We want to move it to the opposite side of the equal sign as our variables, VA, VB, and VC. So we move the -2 amps to the right-hand side of the equal sign, which converts it to +2 amps. And that's what we put in our constant term matrix. Now, let's move along to KCL at node C. So what's our coefficient for VA? And exactly right. So when we make that substitution in, that 0.5 is multiplied by a factor of -VA. So we're going to have -1/2 minus 1/15 for VA. Our coefficient for VB. Anybody have any thoughts on our coefficient for VB? -1/20th. Alrighty, no problem. And our coefficient for VC. So 1/20th, 1/15th, and 1/2, right? Yeah. And there are no constant terms for us to worry about, so we can throw this 0 in. And now we're ready to solve, okay? Now again, we're not actually going to do any of the matrix manipulation that this thing here implies. I just wanted to make it very, very obvious what the coefficients are. By the end of this class period, my best guess is you'll never have to write one of these again. You can literally just look at the equations and glean off what the values for the coefficients that you're going to throw in your calculator are. Just trying to be more formal about it this first time that we're doing it, okay? So I'm going to use the TI-36 here because that's the one I'm more comfortable using. Going to my system solver, this is a 3x3 linear system. And I'm literally just going to type in for my coefficient for VA, 1/10 plus 1/5 plus 1/15, and then let the calculator figure out what that is numerically. I don't particularly care. That's the calculator's job. That's why we're using it. For my coefficient for VB for my first equation, I have -1/5. My coefficient for VC for my first equation, I have -1/15. And my constant term for my first equation is 0. For my second equation, I have -1/5 for VA, +1/5 plus 1/20th for VB, -1/20th for VC, +2 is my constant term, -1/2 minus 1/15 is my coefficient for VA in my third equation, -1/20th is my coefficient for VB in my third equation, and +1/20th plus 1/2 plus 1/15. My coefficient for VC in my third equation, constant term is 0. Solve. I get VA is equal to 1520 over 91 volts, or not in weird fractions, 16.703 volts. VB is 2260 over 91 volts, which is 24.835 volts. And VC is 1580 over 91, or 17.363 volts. These numbers match what I got when I wrote this thing out, I don't know, 5 years ago, so I feel like we did it right. So these are our nodal voltages, VA, VB, and VC. Okay? These are the steps that we use to apply the nodal analysis technique. Now, let's talk about what we can do now that we know these nodal voltages by referring back to our figure. Okay? So now that we have applied nodal analysis, the voltage at node A with respect to ground is known. The voltage at node B with respect to ground is a known quantity. And the voltage at node C with respect to ground is a known quantity. So if I wanted to find the power absorbed by my dependent source, what would that be in terms of my nodal voltages? So we know that there is a current of 0.5 Vx, so that would be 0.5 Vc minus Va, where this represents the current flowing through the dependent source. What's the voltage drop across the dependent source, where the current's flowing into the positive polarity terminal? Positive Vc. So knowing those voltages, we're now able to calculate the power absorbed by this dependent source. What if we wanted the power supplied by the 2 amp source? Anybody have any thoughts? What's the current supplied by the 2 amp source? Not a trick question, it's a 2 amp source. It's 2 amps. Now we need the voltage, where the current is flowing into the negative polarity terminal. VB. Good to go. What if we want the voltage Vx? We've technically already done it, but it's just Vc minus Va. We could use Ohm's law here to find the, with these known voltages, to find any and every current in this circuit. We can use it to find any and every power in this circuit. Once we know these nodal voltages, within 1 to 2 more steps of stuff we've done before, we know literally everything about this circuit. We know the power, we know every voltage, every current, power supplied, power absorbed, all that kind of good stuff within just 1 extra step, okay? So nodal analysis is an incredibly powerful tool because it tells us so much about the behavior of the circuit all in one go. The hard part here is effectively just following the rules, which I've outlined in these various steps, to make sure that we're doing it correctly every time, okay? So one of the things that I see students make the most mistakes about is they forget to do step number 4. You will jump into writing your KCL equations because that's the meat and potatoes of your nodal analysis procedure. And then you'll find out that you don't have quite enough equations to actually solve for things. So that's why I put step number 4, define controlling variables in terms of nodal voltages before you do the KCL part of this procedure. I'm listing the steps in such a way as to help you remember what to do. If you do them in this order, and you get in the habit of doing them in this order, you will never find that you don't have enough equations to actually solve your system, okay? All right, now let's break things by including, Sully. So let's look at this. Let me I've got so much going on here. Let me erase some of these errors, okay? So we want supplied. So we want the current flowing into the negative polarity terminal. And let's call this the current source, okay? Since we're calculating supplied power, we want the current to flow into the negative polarity terminal, right? So V current source is VB because that's the positive, the nodal voltage associated with the positive polarity terminal minus ground, which is the voltage associated with the negative polarity terminal. So that's why we could just write it as VB. Yeah. So it's always going to be positive polarity minus negative. The nodal voltage associated with the positive polarity terminal minus the nodal voltage associated with the negative polarity terminal is the voltage drop across the element. Yep. And then the rules regarding the passive sign convention apply. So if we want supplied power, we want the current to flow into the negative polarity terminal. We want the absorbed power, we want the current to flow into the positive polarity terminal. So if we wanted the power absorbed by the 2 amp source, it would be 2 amps times negative VB. All right. Okay, so any other questions? All right, now we will move along and break things by including a voltage source. Okay. So we're not going to do a full analysis here. I'm going to just explain why voltage sources are problematic, and then we'll move along from there, okay? So let's say that I had part of a circuit that I was looking at, where I had a 5 ohm resistor, an 8 ohm resistor, let's just make this a 10 volt source. This is, doesn't matter, so a 6 ohm resistor and a 2 ohm resistor. And just for the sake of argument, let's call this stuff over here node A. Then we have B, C, D, E, and F, where we're really not caring about what's connected elsewhere, okay? So if we were trying to write our KCL at node B equation, we'd be taking into account this current directed to the left, this current directed down, and this current directed to the right. Well, the one to the left would just be VB minus VA over 5 ohms. Everything's easy peasy there. The one directed down would be VB minus VE over 8 ohms. Then we have the one directed to the right. This is problematic, okay? Because our goal here is to write an expression for the current in terms of our nodal voltages. But we're doing that through a branch that contains a voltage source. What does a voltage source do? It supplies a fixed amount of voltage regardless of the amount of current that is flowing through it, which means there literally does not exist a relationship that we can write to account for this. So what I'm going to do is I'm going to call this current IVS LR because it is a current flowing through the voltage source from left to right. Okay. Now I'm going to set this equal to 0. We are going to run into a similar problem when we write our KCL equation at node C. So we're going to have this current to the left this current down, and this current to the right. So let's do the easy ones first. To the right, we're going to have VC minus VD over 2. Our current directed down is going to be VC minus VF over 6. And then we have the current directed to the left through our current source, or excuse me, through our voltage source. And again, we have no real relationship that we can write. So I'm going to call this IVS RL because it's the current flowing through the voltage source from right to left. So what is the relationship between the voltage source current in green and the voltage source current in red? They are equal but opposite, okay? So how we're going to handle this case, and we're going to have to do this the majority of the time when we have a voltage source, and I'll explain why I'm saying the majority and not all in just a moment, is we are going to add these KCL equations together. The reason why we can do this is rather simple, but so the equation for KCL at node B is equal to 0. The equation for KCL at node C is also equal to 0, and 0 plus 0 still equals 0. So this is a perfectly valid move. We call this a supernode. Okay. So when we combine these two KCL equations, effectively what we are doing is adding together all of the currents that are leaving this supernode containing nodes B and node C simultaneously, with the understanding that the current that's flowing through the voltage source is going to cancel each other out because we're going to have the current flowing from left to right added to the current flowing from right to left, which are equal and opposite. So those terms go away. So we wouldn't do this. We would do KCL at supernode BC, and that would be VB minus VA over 5 plus VB minus VE over 8 plus VC minus VF over 6 plus VC minus VD over 2. The exact same things we would get if we added those individual KCL equations together, okay? So that is the supernode technique, and that's what we're going to have to do for most voltage sources. So now, what we are going to do is analyze a circuit that contains a voltage source and talk our way through another small step that needs to be included, okay? I want to explain where that small step comes from here. So if we write our KCL equation, we get one equation for 2 nodes. We need a second equation. Where do you think it's going to come from? So nobody's saying anything, so I'll just give you the answer. So are you raising your hand or scratching your back? You're exactly correct. So anytime we have a voltage source, we are going to write a voltage relationship equation, okay? Let's put that over here on the right just real quick. So what Hannah has correctly surmised is that we can express the voltage that is provided by the voltage source, 10 volts. I don't know why my screen keeps wiggling so much, but it's bothering me, in terms of our nodal voltages. simply by doing exactly what we did earlier to express a voltage in terms of our nodal voltage, right? So what node is associated with the positive polarity terminal of the 10-volt source? VB. What node is associated with the negative polarity terminal of the 10-volt source? VC. And now, these two nodes have generated two equations, so we're going to wind up with the right number when we do our solving our system, okay? So just to recap here, every time we have a voltage source, we will write a voltage relationship equation. Most of the time, when we have a voltage source, we will write a KCL equation. And when we analyze this next circuit, we'll talk about why it's only most of the time and not all of the time, okay? All right, so the last thing that we're gonna look at today is this circuit. It is going to be large and ugly. All right, so this is our circuit. This is horrifying looking. That being said, you can actually solve this system using one of these crappy calculators. I wouldn't put anything this nasty looking on your exam unless you guys did something to just really piss me off. So we haven't seen anything like this literally ever, okay? But I will show to you guys that we could actually solve this thing just using one of our rinky-dink little $15 calculators, okay? So this circuit obviously contains multiple voltage sources, both dependent and independent. It contains multiple current sources, both dependent and independent. So we are going to have to modify, oh, and I need to define the current IX here, or we're going to have a problem with one of our steps. So we are going to modify our algorithm slightly to include the extra steps that we are going to need, okay? So step number one will still be to identify our nodes. So we have this node at the top left, this node at the top right, this node at the middle left, this node in the middle, this node at the right, and this node at the bottom. Okay. So let's throw some labels on this. So A, B, C, D, E, and F. So before, when we were talking, step number 2, let's go ahead and write that down real quick, is to select our reference or ground node. And before, I had said that whenever you have current sources, or only current sources in your system, your best choice is to select the node that touches the most elements. When we have voltage sources in the mix, our best choice for the ease of math is to select the node that touches the most voltage sources. So which node touches the most voltage sources? F. F touches 2 voltage sources. A and B touch 1, C touches 1, D touches 1, E touches 1, but F touches 2, okay? So we are going to erase this F and choose this bottommost node as our reference, all right? Step number 3 here will be to identify our supernodes. Okay, so supernodes exist only when there are voltage sources, okay? And we use the supernode to encapsulate the voltage source so that the current flowing in and the current flowing out cancel each other, or the current flowing through the voltage source in both directions effectively cancels out. So this is a supernode containing A and B. And this is a supernode containing C, D, and ground. Okay. You may call this a super duper node because it's multiple supernodes agglomerated together. I'm just going to call it one supernode. Okay. All right. So what we're going to do now is step 4. Assign our nodal voltages. So we're going to have VA, VB, VC, VB, VE. That's it. Step number 5. is going to be express our controlling variables. In terms of our nodal voltages. So in this case, all of our dependent sources are controlled by the current Ix, right? Our dependent voltage source at the top depends on the current Ix. Our dependent current source at the bottom depends on Ix. So how do we express Ix in terms of our nodal voltages? So Ix is this guy right here, the current flowing through the 10 ohm resistor. So try again. VD minus VE over 10. Absolutely correct. So the controlling variable isn't attached to the dependent source. It's the thing over the resistor or something like that that's controlling what the dependent sources do. Okay. So VD minus VE over 10 ohms. All right. That's our, yes. Say that louder, please. So you're saying VE is ground? So that's a very good question, and it's a very common mistake. There is a supernode that contains VC, node C, node D, and the ground. But node C and node D still have their non-zero voltages. So they're forming a supernode, but they are not assuming the same voltage at every point along the supernode. And if let's just go back here to look at what we did, right? So when we wrote our equation here for KCL at B and KCL at C, we added the results together. We didn't replace every B with C or every C with B. There are still two different voltages, and there have to be, because we know from our voltage relationship that there is a potential difference of 10 volts between nodes B and C. And we'll get to that exact relationship here in our next step for that large supernode at the bottom. But that is a very, very good question, and it is a very common mistake that students make. So I'm glad you addressed it. Jonathan.
What made you know to put it like that?
The problem statement. I chose it.
Oh.
Yeah. So I chose that the current flowing through that resistor controls other things entirely arbitrarily. Yeah. Any other questions? All right, so we've expressed our controlling variables. Step 6. Is write voltage relationship equations for all voltage sources. And I'm front loading this step again because it's something that I see students tend to forget to do. So if we do it early, we'll make sure that we have all of our equations written, okay? So how many voltage sources do we have? 3. So that means we're going to have 3 voltage relationship equations. Let's start with the top one. How I write these is the voltage provided by the source. So that top one is providing 5 Ix is equal to voltage at the positive polarity terminal, which is VA, minus the voltage at the negative polarity terminal, which is VB. So we would have 5Ix is equal to VA minus VB for our first equation. Yes. No. The controlling variable Ix is the exactly right. So the controlling variable is not the thing that's attached to the dependent source. It's the thing out in the circuit somewhere that's controlling the source. Okay. All right. Now let's work on this 15-volt source on the left. So we're going to have 15 volts is equal to, so what's the nodal voltage associated with node C, or excuse me, with the positive polarity terminal of the 15-volt source? C. What's the nodal voltage associated with the negative polarity terminal of the 15-volt source? 0. So we can say that 15 volts is equal to VC. This is why we choose our reference node as the node that touches the most amount or the most voltage sources, because it gives us free information. We now know that VC has a nodal voltage of 15 volts. We don't have to do anything to find it. Similarly, we could say that 9 volts is equal to VD. Okay. All right. Now, let's move along to step 7. I think in my old notes, I called this step 7A. We're just gonna, and then I had a step 7B. Let's just do step 7 and step 8 because I'm changing it ever so slightly for no real reason. So step number 7 is going to be write KCL equations for all supernodes that do not contain the reference node. Okay. So this is where that we are going to write KCL equations for most voltage sources things comes into play. Okay. So our supernode VC, VD, or CD and ground contains our reference node. And in the nodal analysis procedure, we never write a KCL equation at our ground node. So the only equations that we are going to get from this are our voltage equations. And that's perfectly okay because we have 2 nodes, not including ground, and we already wrote those 2 equations when we wrote our voltage relationships. Writing a KCL here doesn't provide any value to us whatsoever. It wastes time without giving us any useful information. So anytime your supernode contains the ground node, you do not write a KVL equation. The voltage relationship equation is all that is necessary. So our supernode at the top containing nodes A and B does not contain the ground node. So we are going to have to write a KCL equation for that particular supernode. So what that KCL equation is going to entail is us adding this current, this current, this current, this current, and this current together simultaneously. All of the currents that are leaving the supernode get added together in one KCL equation. So KCL at supernode AB is going to be what? So let's start with the current leaving node A and flowing to the left. Alex, what's that going to be? Sully, help him out. Yeah, so the current that's leaving node A and flowing out to the left. So I agree with what you've said out loud so far, VA minus. Let's keep it rolling. So it's the current flowing through the 4 ohm resistor, right? So the 4 ohm resistor is between what two nodes? Okay. So you can go that far and make that substitution, or you don't have to necessarily. So I would write that right now as VA minus VC over 4 ohms. I do all my substitutions in one go at the end. Okay. All right, now we need the current flowing down through the 2 ohm resistor. Lucas Duran, tell me what that current is. Exactly right. VA minus VD over 2. Now I want the current flowing diagonally down and to the right through the 3 ohm resistor. Nick Winkleman, tell me what's up with that. Exactly correct. So those are all of the currents that are leaving the VA side of our supernode. So now we work on the node B side of our supernode. So we need the current flowing down through the 6 ohm resistor. Gregory, tell me what's going on there. So I'm looking for the current flowing down through the 6 ohm resistor. Yeah. Other way around. B minus D over 6, because we're looking for leaving node B as positive. Now we're looking for the current flowing to the right through the 8 ohm resistor. Daniel, tell me what's up with that one. Exactly correct. VB minus VE over 8 ohms. Equal to 0. So I drew 5 currents leaving this supernode. I have 5 terms in my equation. I'm done. Okay. That's the only supernode that does not contain our reference node. So we are done with step 7. Okay. Now we move along to step number 8. Write a KCL equation for all remaining non-reference nodes. Okay. So let's look up here. So we just wrote our equation for supernode AB, our KCL equation for supernode AB. So that one's done. Nodes C and D are part of a supernode containing ground. So we don't write a KCL equation there. So the only node that's left is VE over on the right. So once we write that VE or that KCL at node E equation, we are done. So that's going to be this current directed to the left, this current down, and this current up. Okay. So let's start with the current directed to the left. Let's do it KCL at E. Current directed to the left. Amanda, can you help me out here? Exactly right. VE minus VD over 10. Now let's do the, Brody. You could, but you're going to wind up substituting IX back in later. So I typically, for all my KCL equations, I put everything in terms of my nodal voltages just to make sure that I'm doing it, making sure that I've got everything accounted for. When you are more comfortable with things, you can kind of do whatever the hell you want, as long as you're making sure that everything is taken into account, right? So you are 100% correct that the current that we just referenced is negative IX. All right, current directed up through the 8 ohm resistor. Anna, can you help me out? So I think you said B minus E over 8. We're looking for the current in the opposite direction. Okay, so we're looking for the current directed up. So when we are writing a KCL equation at node E, E is serving as the positive polarity terminal for every resistor that's connected to node E. So we should see VE minus VB over 8 ohms. Slightly too far. Dang it. Lastly, we need the current flowing down through the 5 ohm resistor. Matthew, tell me what's going on there. VE over 5, and that's it. Absolutely correct. Thank you. So we have 1, 2, 3, 4, 5, 6 equations, 6 unknowns. However, everywhere we see IX, we can substitute in things. And everywhere we see VC, we have a 15 volts. Everywhere we see VD, we can substitute that with 9 volts. So this does reduce down to a 3 equation, 3 unknown system. That being said, some of your homework problems will not reduce down to that simple of a thing. So you are expected to have MathCAD installed and know how to use it. For your homeworks and everything, like I said, that's great, but you do need to be able to do this by hand for the smaller systems, or by calculator, I guess would be a better way to put it, for the smaller systems and all of that kind of good stuff. If you do not have MathCAD installed on your computer, please send me an email and I will give you effectively the link and the credentials and all that kind of stuff so that you can log in and have the license so that you can actually use the solve block. If it's been a while since you have had to use the solve block functionality to solve a system of equations and all that kind of stuff, let me know. I will tell you that the in-class assignment solution for today's stuff, I actually include my MathCAD sheet that goes through setting up the solve block and all that kind of stuff and how everything is written. But it doesn't specifically tell you that you need to press Control : to get this specific type of equal sign and all that kind of stuff. So for anyone who needs it, I'm willing and able to help you figure out how to use MathCAD to do this stuff. But I don't want to waste a bunch of time for a bunch of people that don't need it. So anyway, we've done all of the heavy lifting for this particular problem. Now it's just throwing it into a solver of our choice and running with it. So I'm done talking for the day as soon as I answer this gentleman's question. I believe so. I know that we used to, and we switched over to, I think, an Amazon Web Service based thing. I know that that has SolidWorks on it. I'm not sure if the new system currently has MathCAD on it. I'll have to ask Ashley about that. They do. Okay. So yes, but I don't remember what the website or the URL for that is, but I can find it and put it on the course page.